Morning, guys. Our lesson for today is about development of reinforcement. So, development of reinforcement, or simply development-like concepts, is founded on one major assumption, and that is the compatibility assumption. So, this plane section remain plane is actually anchored on strain compatibility. Compatibility assumption, or which is normally stated in terms of the plane sections remain plane uh, rule. So this implies that within this assumption, there is no slippage occurring between the reinforcement and the surrounding concrete. Okay? So if there is a slippage, then this assumption will actually become invalid, since the linear, okay, the linear representation of your strain diagram will no longer be valid. So it means that if there's a steel reinforcement somewhere here at this level, whatever is the stress of the concrete all throughout will demonstrate a linear strain diagram or representation, which is a straight line. Therefore, it's a plane. Okay, representation. So this becomes now a straight line, and this is also straight line. So before the deformation had happened, and after the deformation had happened. So this is now a linear strain distribution diagram that is simply stated in terms of the plane sections remain plane, and is most popularly known as the strain compatibility assumption. So with that, there should be no slippage. Okay, so this steel here should not slip. Okay, so no slippage, or else this assumption will no longer be valid. So there must be enough force to see to it that there is no slippage between the reinforcement and the surrounding concrete. And also, it implies that this must have some forces which are called the band forces that exist between the reinforcement and the surrounding concrete. for this first implication again to be valid. So if there were no band forces, the bars will simply slide or slip relative to the surrounding concrete, and the flexural resistance will simply be the sum of the resistance of each material working independently, and thus the strength will be approximately equal to the strength of a plain concrete section. Okay, so this is now the conclusion coming from these assumptions here. Okay, so let's try to understand it by means of illustration. So it simply illustrates to us that when a beam which is reinforced at the tension side, okay, so these are tensile steel, is loaded by a load, a uniformly distributed load, or any type of loading, okay, in that regard, will actually bend, and therefore this steel here, since the fibers at the bottom, so this is a positive bending, will experience tension, and the fibers at the top will experience compression. So the tendency for this steel is to stretch and elongate, and that would only happen if there's no slip, okay, or slippage somewhere along the tire span. And the weakest point at which slippage may happen is at the ends, okay, so weakest at the ends. So if there's a slip here, it means to say that there is no bond, okay, between the concrete and the steel, and therefore the plane section remain plane, implication will not happen. But if the band forces are enough to resist any slippage to occur, then we can say that the strain compatibility relationship is valid. Okay, so you can see here now the band forces represented by a uniform stress all throughout the tension steel, okay, and these band forces are required to maintain compatibility of strain between the steel and surrounding concrete. So for plain bars, when you say plain bars, these are smooth, undeformed, okay. The band stress is provided by a very relatively weak chemical adhesion and mechanical friction, okay. So since it's smooth and undeformed, there is but a very little chemical adhesion and mechanical friction, and therefore the bond stress is very weak, and at higher loads the bond strength is provided by the interlocking of the natural roughness of the bar and the concrete. But since the plain bars have no roughness, then this natural band is so low, okay, very low, hence it is frequently inadequate to sustain the loads in tension, and therefore failure may arise. So the total loss of the band did not mean collapse, however, but again, as I have said, this will create excessive deflection because the concrete and the steel is not acting together in harmony to resist the loads uh, brought about by the flexural stresses induced internally. Although the provision of end hooks may save the beam from collapsing, and you call that anchorage. So this anchorage can help in one way or the other in the prevention of collapse, but again, it is not a good practice to rely on anchorage alone, but rather the bond stress must always be preserved in order for the beam to act efficiently. So what happens when the bond stress is lost, but there is an end hook? So what happens is that your beam will perform just like a tied arch. Okay, so you look here. Okay, so this is now an arch or a compression arch. And the steel stresses is constant all throughout the unbanded section, which is equivalent to the value at the maximum midspan moment. So this will act like a tie rod or a tension rod. Okay. So steel elongation is very large than in beams where bond is preserved, and this will result in a very large deflection and bigger crack widths. Okay? Therefore, the American Concrete Institute and the NSCP requires, okay, so the basis for NSCP is ACI. So NSCP and the ACI requires the use of a deformed bar, not plain bars, where the bond strength is provided by direct bearing of the reinforcement and the surrounding concrete. So let's move on to some deeper concept on bond stress. So there are two types of bond stress. The first one is the anchorage bond, and the second one is the flexural bond. So for the anchorage band concept, we can represent this better by assuming a cantilever beam. So this is now a cantilever beam. that is loaded as shown. Okay, so take note that the tension is no longer at the bottom, but since this is a negative bending, the tension fibers are on the top, therefore the reinforcement is at the top portion. So this is the tensile reinforcement. And since this is in tension, the tendency for this portion here, wherein the maximum moment is at the face of the support. Okay, so the maximum moment is at face of support. Therefore, at this point, there's a very big tensile force T that is pulling, okay? Pulling this bar from the anchorage. Okay, you call this point here now okay, your anchorage zone. Okay, so this length here, which is L1, will dictate the strength of the bond. Or simply, we can call it the bond stress. So if this length is long, then the bond stress is great or big. If this length is too small, the bond stress is small. Okay? So what is the length of this L1 from point A to point B that will be sufficient for this tensile reinforcement not to be pulled out, okay, before it reaches its yield strength, Fy. Okay, so this length now will give birth to what you call the length of anchorage, or sometimes known as the length of development. Okay, so the length of development or the length of anchorage is simply the length in which the tensile reinforcement will not slip or be pulled out from the anchorage prior to achieving its full strength, Fy. Okay, so remember that. Okay, so the length of development, or simply what you call the anchorage, is the length in which there will be no pull out or no slip or slippage, if you want, prior to achieving Fy. Okay, so if you have reach Fy and then it is pulled out, then you can say that the failure is brought about by achieving Fy rather than by losing the bond stress. Okay, so bond stress now and the length of anchorage are just the same. Okay, the only difference is that in bond stress we are looking for uh, the stress or the strength between the concrete and the steel to prevent pullout, while the length of development and anchorage is we're looking for the length also to prevent pullout. Okay, so they are just the same. We're just using a different context, and I'll show you why is it better to term it the length of development or anchorage rather than band stress later. Okay, let's take a look at the anchorage zone. So I showed you a while ago that this part here, okay, this part here, okay, so is the anchorage zone. So I told you that, no? So the anchorage zone is the point in which from A to B, length L1 is actually obtained. Okay, so this is the length of anchorage, and the bond stress is here. So bond stress and length of anchorage are just the same. Their purpose is just to measure the bond stress or measure the length of anchorage to prevent pullout. And the pullout is caused by a tensile force TB for a single bar. So we are actually demonstrating it in terms of single bar. Okay, so how do we do it? So we just take note of the summation of forces horizontal equals 0. If you call your bond stress letter U, then stress is per area, okay, per unit area. So if I multiply U with the area of one bar, then I can equate it to TB here. Okay, so if we let U is equal to the bond stress, and then the area surrounding this one single bar is simply the perimeter, okay, multiplied by the length. Okay, so if I get the perimeter like this, okay, so surface area is simply the area, okay, which is equal to the perimeter multiplied by the length, okay, L1. Okay, so this is now the area, okay, uh, sorry, the area is the perimeter O, okay, multiplied by the length, and then this is the bond stress. If I multiply stress and area, this will be equal to the tension bar. Okay, the tension on one single bar. But we know that T is equal to ASFS or ABFS. So the area of the bar multiplied by the stress in the bar, where AB is the area of a circle defined by the diameter of the bar dB. Therefore, my perimeter is pi dB and my area is pi dB squared over 4. I simply substitute it here. I get this equation. And if I manipulate this equation here, I will get my final band stress formula, which is FSdB over 4 L1. Okay, so this is the basic bond stress formula. And the required L1 is simply FSdB over 4U. If I invert this in terms of L1, okay, so this is now the length of anchorage. And they are just the same, okay? In terms of concept, bond stress or length of anchorage will just give you the amount to be measured in order to see to it that your tensile bar will not experience any pull out. Okay, so for strength design, we can now replace simply L1 by LD, Fs by Fy, dB dB for UU. Okay, so it's just the same. We only represent it in terms of the strength design parameters, where LD is known to be in general your length of development, no longer the length of anchorage. Okay, so take note that this is now changed from anchorage to the word development. Okay, the word development there is to describe your yield strength, Fy. Okay, to develop the yield strength, Fy. Okay, so that is how we derive, okay, the concept on the length of development. And the reason why we use normally length of development rather than bond stress, because length of development is easily measured in terms of length, while band stress cannot be physically seen in terms of stress. It's very difficult to see a stress in terms of a value, okay? But the length, you can see it. If it's 1 meter, it's 1 meter. If it's half a meter, it's half a meter. So that's why it's better to call it in terms of the length of development rather than the bond stress notation. But as I've said, you can use the term of bond stress if you want. You can use the term length of development if you want. So they just mean the same thing. Okay? So I'd like to stop at this point to hear some of your concerns if there are any. So we'll continue on the flexural band concept in tension and compression on the next video. Thank you very much.